So when we discussed shortest path algorithms, we have we said that the shortest path problems are solvable in polynomial time, but the longest path problem is NP hard. So if you take a DAG, that's a directed acyclic graph, the shortest path as well as the longest path can be computed in linear time. When we say linear time, it's the linear in terms of the number of vertices and number of edges in the graph using the DFS. Let's quickly look at how to do this in this video. So in this video, we're going to study how to find the longest path and shortest paths from a source vertex to every vertex in a directed acyclic graph. Just to quickly recall, DAG is a directed graph which does not contain a cycle, and so we're going to find the shortest path and the longest path from a source vertex to every node in this DAG in linear time. Quickly, just to even recap, the topological sort is the listing of the nodes in the DAG in the decreasing order of the finish times after you apply the DFS on it. The way to compute this was that we initialized the DFS, and then when the vertex is finished, when you find the finish time of the vertex, this should have been u. So when you find the finish time of a vertex u, you keep adding that into a list. Okay, so at the end of this algorithm, the list of vertices in L will be from left to right will be in the decreasing order of the finish times. So once you compute the this topological sort, then we know that there will be only forward edges. Forward edges means the edges from left to right. After this topological sort, there will be no backward edges if the given graph is a DAG. So now it's easy to find the longest path as well as the shortest path. So we have two variables. L will keep track of the longest path. S will keep track of the shortest path. Pi1 is the which will keep track of the predecessor vertex in the case of a shortest path. P2 is the one which will keep track of the predecessor vertex in the case of the longest path. So S is the source vertex. The longest path from S to S itself is 0. Shortest path from S to S itself is also 0. The pi function of both the longest path and S is set to S minus 1. Now you start traversing the list from left to right in the topological ordering. L of I will give you the first vertex which has the maximum finish time after I applied the BFS before you come here. So before this algorithm is called, you applied the DFS on the graph and found the list of all the vertices in the decreasing order of finish time. That list is being maintained in L. So you take the largest finish time vertex, then you do exactly what is known as the edge relaxation. You find whether the shortest path to V is greater than the shortest path to U plus weight of this edge. If the shortest path to V is greater than the shortest path to U plus weight of this edge, then update your shortest path to V, which is equal to shortest path to U plus weight of this edge. Then update your pi function. This should have been pi1 of V should be U. Similarly, if the longest path is shorter than the longest path to U plus weight of this edge, then you can update your longest path to V is equal to longest path to U plus weight of this edge, and then you can update your pi function to be pi2 of V to be U. So what we are essentially doing is that considering the vertices in the topological sort from left to right and relaxing these edges. What do we mean by the relaxing edges? If you are computing the shortest paths, the weight of the shortest paths to V, if it is greater than the weight of the shortest paths to U, update the shortest paths to V to be weight of the shortest path to U plus weight of the weight of this edge U to V. In the case of longest path, instead of greater than, you will have the less than symbol, and we exactly continue. Let's look at this example that we have. So these are the edge weights that we had in the original graph. If you do the topological sort, we know that we get the L as 0, 1, 2, 4, 3. Now let's try to apply this longest path and shortest path on this. Let's take the first vertex. Let's say that we want to find the longest path and shortest path from 0. So I set my longest path to 0 and shortest path to 0 as 0, 0. Now I take the first vertex here in the list, which is 0, and then relax the edges which are outgoing from here. So when I relax the edge 0 to 1, so what happens is that the longest path and the shortest path to 1 will become 2. The longest path to 0 from 2 will become minus 4. Both the longest path as well as the shortest path will become minus 4. Because the longest path now is to 1 is maximum, which is infinity. But right now, so this will be 0 plus 2, which is 2. Max is greater than 2. So the shortest path to 1 will be updated to 2. Similarly, the longest path to 1 right now is minus infinity. So the longest path to 1 will be minus 0 plus 2, which is greater than minus infinity. So we will end up updating the longest path to 1 and 2. So when you relax the edges outgoing from 0, the shortest path to 1 and the longest path to 2 will be updated as 2, 2. So next we will look at the edge in next vertex in the topological sort, which is 1. We will look at the two edges outgoing from here and update the longest path and the shortest path. When you consider the edge 1, 3, the longest path also will be updated to 10 and the shortest path also will be updated to 10. In the case of 1, 2, the longest path right now is minus 4, but the longest path to 1 is 2, and if you add this edge it becomes 3. So the 5 is greater than minus 4, so the longest path to 2 will be updated to 5 from 4. Whereas the shortest path to 2, right now the shortest path is minus 2, but the shortest path to 1 is 2 plus 3. So this is bigger than the minus 4. The shortest path to 2 will not be updated, whereas the longest path to 2 will be updated to 5. So this is what happens after you relax the edge going from 1. Now if you relax the edge going out from 2, there is only one edge which is going out from 2, that is to the vertex 4. The longest path to vertex 4 will be the longest path to vertex 2, which is 5, minus plus the weight of this edge 2, 4, which is minus 1. So the longest path to 4 vertex will be updated to 4. The shortest path to 2 is minus 4. So the longest path to 4 will be updated to minus 4 minus 1, which is minus 5. Right. So the shortest path right now to the vertex 4 is minus 5. The longest path there is 4. Now the next vertex that is going to be considered is 4 in the topological sort. Now there is only one edge which is outgoing from 4. So if you consider this edge, right now the longest path to the vertex 3 is 10. Now if you take the longest path going through the vertex 4, the longest path to 4 is 4 plus 5 will be only 9. But the current the longest path to 3 is 10, which is greater than 9. So the longest path to 10 will remain as longest path to 3 will remain as 10. But whereas the shortest path to 3 right now is 10, but if you consider the shortest path going through the vertex 4, till 4 the shortest path is minus 5. So when you add the weight of this edge, so this becomes 0. So 0 is smaller than 10, so the shortest path to the vertex 3 will be updated to 0. So you can see that the longest path to the vertex 3 from 0 is 10. So that is through the vertex 0, 1 and 3. But if you want the shortest path, so what you do is that from 0 you come to 2, from 2 you go to 4, and from 4 you go to 5. That is the shortest path whose weight is 5. Since in summary what we can do is that so we can both find longest path and shortest path in the DAG by applying DFS first. Once you apply the first time DFS, what you get is a topological sort. After that, consider the edges from left to right and try to relax the edges. When I say that relax the edges in the case of shortest paths, if the newly discovered path, that is the shortest path to u plus weight of this edge is smaller, then update your shortest path. In the case of longest path, if the new path that you are considering is bigger than the longest path that you already have, update your path. The claim is that this gives you both the shortest path and the longest path. let's quickly look at the proof for the shortest path. Okay, the important thing is that we are considering the topological sort of a DAG. Since it's a DAG, you will only have edges from left to right. In other words, from forward edges, but there will be no backward edges. In other words, there will be no backward edge. There will be no edge from your right side a vertex to the left side vertex. Okay, so the proof is by induction. So this is the starting vertex. The longest path and the shortest path to this itself is 0. And if you consider any vertex before this, none of these vertices are reachable from S because there is no backward edge. So the longest path and the shortest path will continue to be minus infinity, and the shortest path will have the values of infinity, indicating that there is no path to any of these vertices which comes before this. So now on the right hand side vertices, so when you compute S of V, so after you relax the vertex V in the topological ordering, you start relaxing the S and you relax all these vertices which are to the left of V before you relax the vertex V. When you come to the vertex V, the claim is that you have found the shortest path to V correctly. The proof is by induction. So when you are at S, the shortest distance to S itself is 0. Now when you come to this particular vertex, this will only have incoming edges from the left hand side, and by induction the shortest path to all the vertices on the left hand side have been computed correctly. So when after you went to these vertices on the left hand side, once you have the shortest path to these vertices correctly, then you have relaxed all the edges which are outgoing from those vertices. So when you visit this vertex V, all the incoming edges have been relaxed because all the edges are coming from the left hand side of this particular vertex V, and by induction you know that you have found the shortest path to all the vertices to the left of this vertex. So and you have relaxed all the vertices which are coming to this particular vertex. So this completes the proof that you have this computes the shortest path to the vertex V correctly. The proof for longest path will follow similarly. So what we have done is that we found the topological sort of a DAG, then we considered the vertices in the increasing order from left to right in the decreasing order of the finish times and relax these edges. By this method we can find the shortest path as well as longest path in a DAG in linear time, because we applied DFS once that take order m plus n time, then we considered every edge exactly once and relaxed them. So that second part of the algorithm also takes order m time. So the total complexity of this is order m plus n, which is linear in the number of edges and number of nodes of the graph. So just to quickly summarize, we found the topological sort of a DAG. After we found the topological sort of a DAG, we considered the order in the topological sort and try to relax the vertices in order to find the longest path and the shortest path in the DAG from a source vertex. We can find the so this algorithm works even when there are negative weights, because this algorithm did not use the fact that the weights has to be positive. Okay, so even when there are negative weights, both the shortest path and longest path from a source vertex to every other vertex in the graph, in the case of a directed acyclic graph, can be found in linear time. So this is in contrast to what we have studied, that in a churning graph the shortest paths are you can find the shortest path in polynomial time, but the longest path problems are harder to find. So that's what we have in this video. So we'll come back with another application of DFS in the next class.